Here we are. We are starting with the description of the Sentinel-2 data. And in order to proceed with this description, I've opened the web browser in which you see I search for this S2 mission that stands for Sentinel-2 mission in Sentinel Wiki. So, I mean, this is the way in which you can get all the information concerning the Sentinel constellation description. So let's go to this Sentinel wiki, okay? And you see here we are going to the Sentinel-2 mission. I will just give you a very brief description, just highlighting what is very interesting for us, especially the spectral resolution and the characteristics of the sensor. So, starting with the overview of the Sentinel mission, we know that it's Sentinel-2 is formed by a couple of different satellites, and on board of these satellites as payloads we have an instrument that is called MSI, that stands for multispectral instruments. Okay, this constellation is done by two different satellites, as I mentioned, the Sentinel-2A and the Sentinel-2B. They were launched using the European Vega launcher, and these couple of satellites have a lifespan of around 7 years, but all the batteries and propellants have been provided to accommodate at least 12 years of operation. So the two Sentinel-2 satellites operate simultaneously, phase at 180 degrees to each other in a sun-synchronous orbit with an altitude, a mean altitude that you see here, it's around 786 kilometers. So that means that they are working, doubling the, as we will see, the temporal resolution, having two satellites that are acquiring the same kind of data because they have on board the same MSI instruments. The MSI, the multispectral instruments, is a passive sensor, and you can see here what is the design and what is able to acquire. And this is the schematic view of the spacecraft with the solar panel and all the instruments in this kind of boxes here. And concerning the orbits, we already mentioned the fact that they have an orbit separation of around 180 degrees, and they have an orbit inclination of 98.6 degrees. That means that are not really polar, but they are inclined of around 8 degrees on the polar. And the mean local solar time, the what is called MLST, is the descending nodes is around 10:30 a.m. That means that the images are acquired around this local time. All right, that is very important for us, and this is the table that is describing the main characteristics of our satellites. That means this is the altitude, this is the inclination, this is the period. That means that every around 100 minutes is completing a single orbit, and the cycle is 10 days. What does it mean? That at the equator, the satellite is passing over the same area every 10 days. That means that we have a repetition time of around 10 days, and this passing always at the same local time, that is around 10:30 a.m. Okay, this is the geographical coverage. Of course, it's acquiring for the most part of the worlds in which we are interested, and these are the different passes. Concerning the MSI instruments, this is the instruments, this the picture of the instruments. but this is not very important for us, because what is very important is the way in which is acquiring data. So that means that this is a push broom sensor, so it's acquiring every single line for every single bands, and this is not a table that in which we are very interested, and this is something that I will explain in the theoretical part concerning the radiometric characteristics of the images. But what is very important is the acquisition resolutions. So from the temporal point of view, the temporal resolution is around 10 days for every single satellite. That, considering that we have a couple of satellites, these revisited times is reducing up to 5 days. So every 5 days we can theoretically have an image over the same area. Concerning the spatial resolution, we will see that the spatial resolution is different for the different spectral bands, and is ranging from 10 meters to 60 meters, while the spectral resolution that is related to the different spectral band is what is the hyperlink here. So we can go to the hyperlink. So from this point of view, we have bands at 10 meters, and in particular we have 4 different bands that are, out of these 4, 3 are the classical RGB bands, that is the blue bands around 0.49 microns, the green bands that is around 0.56 microns, and the red that is around 0.66 microns. And we have, in addition, an infrared band that is the center wavelength is around 0.83. Then we have 6 different bands at 20 meters that are more narrow bands, and you can understand why. And these are divided in the different part of the electromagnetic spectra. In particular, that are calibrated for the vegetation red edge spectral domains that you see. It's around 0.70, 0.74, 0.78 and 0.26 microns. And in 2 different bands we have the mid-infrared bands that are pointed around 1.61 and 2.19 microns, that are particularly interested, for example, for snow, ice, and vegetation moisture and whatever. So we have 6 bands here, and then we have 3 more bands at 60 meters that are focused towards cloud screening and atmospheric corrections. These 4 bands are centered in 0.44 microns, that is a blue band for aerosol, and 0.94, that is the near infrared for water vapor. And then we have a band that is is used for the cirrus detection, that is in the mid-infrared, that is 1.36 microns. So this is the table that are listing the different spectral bands. The 4 bands in the visible. Pay attention to the naming, or better, to the numbering of these bands, because you see these 4 bands that are 10 meters, blue, green, red, and infrared, are numbered from 2, 3, and 4, for 2 for blue, 3 for green, and 4 for red, and the 8th one, the number 8, is the near infrared, 10 meters. Then you see they have a different numbering for the 6 bands of the 20-meter dataset, that is the band number 5, 6, 7, 8A, 11, and 12, that are respectively 5, 6, and 7. There are bands that are the red edge, and this numbering is I mean, in line with the numbering of the 10 meters, because after the number 4, we have 5, 6, and 7. Then we have the 8 that is 10 meter, while the 8A that is, you see, not really the same of the 8 at 10 meters is again in the near infrared. And then we have 11 and 12 that are the mid infrared. While for the 60 bands, 60 meter bands, we have the number 1 that is 0.44, the number 9 and the number 10. So I mean, in terms of numbering, the number is coherent with the wavelength. So the band number 1 is the first one in taking into account the wavelength. You see 4.44 microns, while the band number 2 is 0.49, band number 3 is 0.55, and the last one, that is band 12, is 2 microns, 0.20. So I mean, the numbering is coherent with the wavelengths. Coming back, I mean, the radiometric resolution. The radiometric resolution is the registration of the incremental level of intensity or reflectance that is coming from the ground. And so, I mean, if you are going to the radiometric resolution part of these sites, let me check if it's working. Okay, this is the representation of the spatial resolution. Let me zoom in these things here. Okay, so you see, you can get in a representation in which you can see the electromagnetic spectra, the amplitude of the different bands. These are the band number 2, 3, 4, and 8 at 10 meters. Then you have the others. You see that there are bands that are very narrow in wavelengths, and there are bands, for example, the last one, the 12, that is very large concerning the spectral interval, and these are the band and 60 meters. All right. So from the radiometric point of view, I mean, the radiometric point of view is concerning the possibility to memorize the signal that is coming from the ground. I mean, the radiance that is coming from the ground. And from this point of view, the Sentinel-2 instruments acquire measurement at 12 bits of radiometric resolution. That means that, I mean, we have a digital number enough in order to represent in a very good way the radiance that is coming from the ground. If we are going to the different products, and this is quite interesting concerning the NSI products overview, this is the representation. You can have a look to that. But I mean, usually every single scene you see is representing a square of 110 kilometers times 110 kilometers, so a very square image that is representing this species on the ground. That, of course, if we are talking about 10 meters resolution, that will be made by 11,000 times 11,000 cells for every single image matrix. And we have a naming convention. You know how to download the data from the special video that I share with you concerning how to download Sentinel-2 data. And just to understand which is the naming convention, you see that this is the naming convention. This is what I'm pointing here, in which, I mean, the different pieces of the name are representing the mission, and in particular the date and the hour of the acquisition. So, for example, you see this file name is representing a data that is acquired by the platform Sentinel-2A with the sensor MSI at the level of correction 1C, and the acquisition is done, in this case, the 5 of January 2017 at this particular local time, in which then you have all the different processing baseline number the relative orbit number, because the orbits are also numbered in a geodetic reference, the time number fields, and the processing, the product format, that is the format in which is product. So I mean, you have these things here. When you are downloading the data, so this is the description, I mean, you know that we need, and I'm just scrolling these things here. When you are downloading the data, this is the schema. You are going to an S2 product, a Sentinel-2 product, and all the your data, what you are downloading from the official sites of the Sentinel data, you see is split into these different folders. So the auxiliary data, the data strip, the granule, and whatever, and we can find the data in the granule folder, in which you can have all the bands, but also the metadata and the header file, that is what we are using as described in the part in which I'm uploading Sentinel-2 data in Envy with the particular procedure that Envy is using just for automatically open this kind of external file. So I mean, is defined in this part here. Okay, what we have to lastly to simply describe, then of course you can go through in more detail of these documents. This is the processing level, and the processing level is very important because to the users, Sentinel is deployed in two different processing level, that is called the level 2A and what is called the level 1C. The level 2A is what is most used because the level 2A products provide atmospherically corrected surface reflectance, what is called SR, that are derived from the level 1C product. So I mean, this is classically what is called this reflectance at the BOA reflectance, so bottom of the atmosphere. This correction is what we can get just close to the surface that is acquired. So I mean, without any interference of the atmosphere. So I mean, what we get, I mean, the digital number that we get in this image is representing and is proportional to the reflectance or emittance that is coming from the surface. While the level 1C, so again here, bottom of the atmosphere, just close to the Earth's surface, while the level 1C is what is called the TOA, so the top of the atmosphere reflectance, in which, I mean, here we have the reflectance or emittance, the radiance that is coming from the Earth's surface, plus the contribution that is coming from the atmosphere. So I mean, the top of the atmosphere is the radiance that is coming from the ground, but also what is scattered or reflected by the atmosphere. So I mean, we can get this couple of data. Of course, if we are interested in monitor or in representing surfaces on the ground, we should go to this level of correction, that is the 2A, while if we want to understand if there are any interference with the atmosphere, or we want to take into consideration the scattering of the atmosphere, because we want to use maybe some atmospheric correction models that are more suitable for our application, we should use this L1C. In our course, we will use ever and always L2 correction. So this is enough for the description of the data. So thank you very much, and we will see you for another video.